When transitioning from isolated power systems to ground fault circuit interrupters, or GFCIs, in a surgical setting, the choice of flooring material becomes a critical consideration. ANSI/AAMI Standard ST75 2006/R2010, which is a comprehensive guide to electrical safety in healthcare facilities, equipment, and systems, offers detailed guidance on selecting appropriate flooring. The primary concern is ensuring a low-resistance path to ground, which is crucial for the proper functioning of GFCIs and for minimizing electrical hazards. In the context of changing from isolated systems to GFCIs, the existing flooring might need to be upgraded. The key parameter is the resistance of the flooring material. It should provide a path to ground with a resistance of less than 100,000 ohms. This low resistance is essential for the GFCI to quickly detect a fault and interrupt the circuit, thus preventing an electrical shock. If the current flooring already meets this requirement, an upgrade may not be necessary. However, it's imperative to verify this through proper testing and assessment. Several factors influence the flooring's resistance. These include the material composition, its thickness, the presence of any coatings or finishes, and the environmental conditions, such as humidity and temperature. Different materials exhibit varying levels of conductivity. For instance, certain types of conductive vinyl or epoxy flooring are specifically designed for use in areas where static control and grounding are critical, such as operating rooms. These materials typically incorporate conductive elements that facilitate the flow of electrical current to ground. In contrast, standard tile or carpet may not provide a sufficiently low resistance path and could potentially impede the proper operation of the GFCI. The thickness of the flooring material also plays a role. Thicker materials generally offer higher resistance than thinner materials of the same composition. Any coatings or finishes applied to the flooring can also affect its conductivity. Some coatings may enhance conductivity, while others may act as insulators, increasing the resistance. Environmental conditions can also influence the flooring's resistance. High humidity levels can increase conductivity, while dry conditions can decrease it. Therefore, it's essential to consider these factors when evaluating the flooring's suitability. Proper testing is crucial to determine whether the flooring meets the required resistance standard. This typically involves using a megameter, also known as an insulation resistance tester, to measure the resistance between the flooring surface and a designated ground point. The test should be performed under typical operating conditions to accurately assess the flooring's performance. It's also important to consider the installation of the flooring. Proper installation techniques are essential to ensure consistent conductivity and prevent the formation of gaps or seams that could impede the flow of current. Flooring should be bonded to the building's grounding system to provide a reliable path to ground. This bonding should be performed by a qualified electrician in accordance with applicable electrical codes and standards. Furthermore, regular maintenance is necessary to maintain the flooring's conductivity over time. Cleaning with appropriate cleaning agents and avoiding the use of harsh chemicals that could damage the flooring material are essential. Periodic testing should also be conducted to verify that the flooring continues to meet the required resistance standard. The rationale behind the low resistance requirement is rooted in the fundamental principles of electrical safety. In a properly grounded electrical system, fault currents, which are unintended currents that flow outside the normal circuit path, are safely conducted back to the source, causing the overcurrent protective device, such as a circuit breaker, to trip and energize the circuit. This prevents the fault current from flowing through a person who might come into contact with the energized equipment, thus preventing electrical shock. GFCIs operate on a similar principle, but they are much more sensitive to fault currents than standard circuit breakers. A GFCI continuously monitors the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, the current in both conductors should be equal. However, if a fault occurs and some of the current leaks to ground, the GFCI will detect this imbalance and quickly interrupt the circuit, typically within a fraction of a second. This rapid response time is crucial for preventing electrical shock, as even a small amount of current can be dangerous if it flows through the human body. For a GFCI to function effectively, there must be a low resistance path to ground. This path allows the fault current to flow back to the source, enabling the GFCI to detect the imbalance and trip the circuit. If the flooring has high resistance, it will impede the flow of fault current, potentially preventing the GFCI from operating correctly. In such a scenario, a person who comes into contact with the energized equipment could receive an electrical shock. The specific requirements for flooring resistance in surgery rooms are often dictated by local electrical codes and healthcare facility standards. These requirements may vary depending on the jurisdiction and the type of procedures performed in the surgery room. It's essential to consult with a qualified electrician and review the applicable codes and standards to ensure compliance. The ANSI/AAMI standard S75 2006/R2010 provides valuable guidance on electrical safety in healthcare facilities, but it's not a substitute for professional engineering judgment and compliance with local regulations. In addition to the flooring requirements, other electrical safety measures are also important in surgery rooms. These include the use of isolated power systems, which are designed to limit the amount of current that can flow to ground in the event of a fault, regular inspection and testing of electrical equipment, and proper training of healthcare personnel on electrical safety procedures. Isolated power systems, while traditionally used in operating rooms, are not always required when GFCIs are implemented. The choice between isolated power systems and GFCIs depends on a variety of factors, including the type of procedures performed, the risk assessment, and the budget. Isolated power systems offer a higher level of protection against electrical shock, but they are also more expensive to install and maintain. GFCIs provide a cost-effective alternative, but they may not be suitable for all applications. The decision to switch from isolated power systems to GFCIs should be made in consultation with a qualified electrical engineer who can assess the specific needs of the healthcare facility. When upgrading the flooring material, it's important to consider the long-term cost of ownership. Conductive flooring materials may require special cleaning and maintenance procedures, which can add to the overall cost. It's also important to choose a flooring material that is durable and resistant to wear and tear, as frequent replacement can be expensive. In summary, when changing from isolated systems to GFCIs in the surgery room, careful consideration must be given to the flooring material. The flooring should provide a low resistance path to ground, ideally less than 100,000 ohms, to ensure the proper functioning of the GFCIs and to minimize the risk of electrical shock. Proper testing, installation, and maintenance are essential to maintain the flooring's conductivity over time. Consult with a qualified electrician and review the applicable codes and standards to ensure compliance. Furthermore, remember that GFCIs only protect from line to ground faults, not line to neutral faults. The ground fault protection works by detecting an imbalance between the current leaving on the ungrounded conductor and the current returning on the grounded conductor. If there is a difference of 5 mA or greater, the GFCI is designed to open the circuit within a fraction of a second. Now, let's delve into some additional details regarding the selection and maintenance of flooring in surgery rooms when using GFCIs. Firstly, consider the specific type of conductive flooring. There are several options available, including conductive vinyl, conductive epoxy, and static dissipative tile. Each material has its own advantages and disadvantages in terms of cost, durability, and ease of maintenance. Conductive vinyl is a popular choice due to its relatively low cost and ease of installation. It typically consists of a vinyl sheet with conductive particles embedded throughout the material. Conductive epoxy is a more durable option that is often used in high-traffic areas. It provides a seamless, monolithic surface that is resistant to chemicals and wear. Static dissipative tile is another option that offers good durability and resistance to wear. It is typically made of ceramic or porcelain with conductive additives. Secondly, ensure proper bonding and grounding. The conductive flooring must be properly bonded to the building's grounding system to provide a reliable path to ground. This bonding should be performed by a qualified electrician in accordance with applicable electrical codes and standards, such as the National Electrical Code, or NEC. The NEC specifies the requirements for grounding and bonding of electrical systems in healthcare facilities. Thirdly, implement a regular maintenance program. Regular cleaning and maintenance are essential to maintain the conductivity of the flooring over time. Use cleaning agents that are specifically designed for conductive flooring and avoid the use of harsh chemicals that could damage the material. Periodic testing should also be conducted to verify that the flooring continues to meet the required resistance standard. This testing should be performed by a qualified technician using a calibrated megometer. Fourthly, consider the impact of humidity. Humidity can affect the conductivity of the flooring. High humidity levels can increase conductivity, while low humidity levels can decrease it. Therefore, it is important to maintain a stable humidity level in the surgery room to ensure consistent performance of the flooring. Fifthly, be aware of potential sources of contamination. Contaminants such as dust, dirt, and spills can accumulate on the flooring and reduce its conductivity. Regular cleaning and maintenance can help to prevent contamination and maintain the flooring's performance. Sixthly, consult with the flooring manufacturer. The flooring manufacturer can provide valuable information about the proper installation, maintenance, and testing of the flooring material. They can also provide guidance on selecting the appropriate flooring for your specific application. Seventhly, consider the aesthetic requirements. While electrical safety is the primary concern, it is also important to consider the aesthetic requirements of the surgery room. Choose a flooring material that is visually appealing and complements the overall design of the room. Eighthly, document all testing and maintenance activities. Maintain a record of all testing and maintenance activities performed on the flooring. This documentation can be helpful for troubleshooting problems and for demonstrating compliance with regulatory requirements. Ninthly, train personnel on proper procedures. Train all personnel who work in the surgery room on the proper procedures for maintaining the flooring and for preventing electrical hazards. This training should include information on the importance of grounding, the proper use of cleaning agents, and the procedures for reporting any electrical problems. Tenthly, stay up to date on the latest standards and regulations. Electrical safety standards and regulations are constantly evolving. Stay up to date on the latest changes and ensure that your facility is in compliance. In addition to these considerations, it is also important to address the potential for static electricity buildup. Static electricity can be a hazard in surgery rooms, as it can ignite flammable anesthetics and damage sensitive electronic equipment. Conductive flooring can help to dissipate static electricity and reduce the risk of these hazards. In conclusion, selecting and maintaining appropriate flooring in surgery rooms when using GFCIs requires careful consideration of several factors, including the type of flooring material, proper bonding and grounding, regular maintenance, humidity control, contamination prevention, manufacturer recommendations, aesthetic requirements, documentation, personnel training, and staying up to date on the latest standards and regulations. By following these guidelines, you can ensure the safety of patients and staff and prevent electrical hazards in the surgery room.